This thing gave me, we had issues, but it recorded. Are we recording? Okay. So today we're going to be doing tests on P. So the idea is there is a claim out there that you want to prove or dispute. Now I'm going to give you a really simple example. Let's say there was an opinion poll taken, and you talk to your friends, and you know how people feel, and maybe you're very social and you talk to everybody. You talk to perfect strangers about politics, and your gut feel is that people feel a certain way, and then you hear this opinion poll on the news that's completely different from what your experience tells you. Does that make sense? It's way, way different than what your experience is telling you, and you're saying, I don't think those numbers are accurate at all. Could you test it? You can't demand to see their data. They're not going to show you, but could you go out and do your own thing and test it versus them? I'm going to give you a really simple example of when this happened. Qualcomm Stadium used to be called Jack Murphy Stadium for many, 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 many years. And it was old and run down, one of the worst stadiums in the whole National Football League. In fact, it was one of the last dual-purpose stadiums where they did football and baseball. It was raggedy and run down. And we had a Super Bowl in the late 80s in San Diego. And the NFL told San Diego, we're never having another Super Bowl unless you guys build a new stadium or make this one modern and updated. And it was old and decrepit. So the city leaders at the time convinced San Diegans that we wanted this. So they spent, at that time it sounded like a lot of money. It was like $60 or $70 million on stadium improvements. That really didn't go very far, and then we never did get another Super Bowl, by the way. But the problem was, but the funny thing was, I knew the mayor personally, because I taught her daughter in high school for 3 years. And the city attorney I went to high school with in a small high school in Santa Cruz, I knew both of them. And they weren't bad people, but they basically said things on the news that weren't exactly true or ethical. They said that it was something like close to 70% of San Diegans approved the money being spent on this stadium. And I knew that wasn't true. In fact, I couldn't find any person who thought this was a good idea to spend our money, your tax dollars, on a stadium that you're never going to get to go to just so we can get a Super Bowl. So they pumped all of this money into the stadium, and we never did get another Super Bowl, by the way, because it was still the worst stadium out there. But the point is that so I had my stats class actually do this. The city attorney and mayor came out and said that somewhere around 70% of San Diegans approved this, which would be overwhelming. But the actual numbers were probably much less than 50%. So I had my students actually do their own informal polls. Ask as many people as you can. And of course, we're lazy. We ask our friends, our neighbors, our relatives, But I had a class of 40 people, and every single person came back with quite a bit of data, and not one of them were close to 50%. Now, would this be a scientific proof? Well, probably wasn't a very unbiased poll, for one thing. But this is what we're looking at today. How do you dispute when somebody makes a claim about probability? So we're gonna keep it really simple. All right? We're going to talk about something far more important than politics, right? We're going to talk about free throws. Why free throws? Because they're really easy to measure, and it's just straight up probability. So Graham says, I'm an 80% free throw shooter. Now, we have to decide, when we're looking at this, remember I said rarely in life are things actually equal. I said most things are actually inequalities. So when Graham claims to be an 80% free throw shooter, and he goes out and he shoots 90%, do we say, he's lying? Or is it okay to be better than you say you are? If he goes out and shoots 50%, now we're going to say, no, we don't believe you. Does everyone understand? There's an inequality here that's implied. So if he says he's an 80% free throw shooter, what's he really saying? At least. He wouldn't be at most. Because if he says I'm at most 80, then he could miss every single shot, and he'd be telling the truth. Does that make sense? You go, yeah, that's not going to work. So there's an implied inequality here when he says he makes 80%, that it's at least 80. And the reason is when we set up our null and alternative hypothesis, they really should be complements. They really should cover all areas. Now, in the stats books, they don't do this. In the stats books, they'll say the null is equal and the alternative is less than. Well, the problem with that is, what if he goes out and shoots better? We don't have a slot for that. That's not even a possible outcome if we do it that way. So it's safer to do it this way. Okay? So the null hypothesis and the alternative hypothesis. The null is that P is equal? No. Greater than or equal. So therefore, what's the alternative?
It's less than.
Less than. So we're looking at the following situation. We're only going to reject the null hypothesis if it's extreme in the left tail. And again, let's say Graham really is an 80% free throw shooter, but he goes out and shoots, 2 shots and makes 1 of them. That doesn't disprove he's an 80% free throw shooter. That's not enough evidence. He goes out and shoots 100 shots and makes 70 of them. Is that even enough evidence? We don't know yet. We'll look. Again, I'll go back to, Steph Curry. Greatest free throw shooter I've ever seen. But I've actually seen him miss 2 in a row. So does that all of a sudden mean he's not a 90% free throw shooter because he missed in a small window? No, if we step back and look at his last 100 or last 1,000, we see a high percentage. So if somebody is actually an 80% free throw shooter, does that mean they absolutely always make 8 out of every 10 shots? No, he's going to make 8 out of 10, 5 out of 10, 10 out of 10, 9 out of 10. Overall average would be 8 out of 10. So in a small sample, it's okay to be a little less, a little more. What we're saying is, no, you got to be a lot less before we say, no, there's no possibility. Okay? How do I know? It's always the direction of the alternative that will cause rejection. Now, we want to test, since this is not life or death, at the 5% level. There's really only 2 tests we ever do, 5% and 1%. Right? If this was the FDA approving a cancer treatment or something, we'd probably go with 1%. But this is Graham shooting free throws. Probably the fate of the universe isn't resting on whether you make them or not. We'll go with 5. It's safe. All right? So what we need to do is figure out now the criteria for rejecting the null hypothesis. What would cause us to reject? Well, first of all, what is the z-value for a 5% tail? Because we're looking at all of it being in this tail. So what is this z-value right here? First of all, is it positive or is it negative?
Negative.
It's negative. Oh, so the z-value is a positive number. When we look up the z that goes with a 5% tail, that's one of your magic numbers. Which one is this one?
$1.96.
No, that's 0.25.
Oh, 1.645.
645, yeah. Now, that's just the z-value. We're going to use the negative because we want left tail. If we wanted right tail, we'd use the positive. So this is not the most important part of the problem, but this is the part that people make the most mistakes on. It's called the criteria for rejection. This is not a calculation. I'm just basically saying out loud, where is the line in the sand? Okay? And we say it like this. We will reject the null hypothesis if our calculated value of z, I like to call that z star, is what? It's got to be that way. So bigger than or smaller than?
Smaller than negative 1.645.
Beautiful. Perfect. Everybody got it? 1.645 is the number I'm using, but since it's a left tail, I got to be more negative than the negative. If it were right tail, I'd have to be more positive than the positive. So my line in the sand is if his results come in to the left of that. Now, by the way, we do all of this before we actually do a sample. There's a common error in life. In science, this does happen. Thank you, Dylan. I collect a bunch of data, I do a bunch of tests, I do all this, and now I'm going to formulate my theory. Doesn't work that way. Yeah, so the government's going to pay you millions and millions of dollars to do research. You're just going to collect a bunch of data with nothing in mind, and when you're all done, now you'll come up with an idea of what all this data was for. No, I don't think it works that way. No, you have an idea, and you believe something's a certain way, so what do? You go out and you collect all your data to see if you're right or if you're not right. You don't formulate your hypothesis after the fact. You have your hypothesis first, and then you collect your data to see. I have a cancer treatment, and I think it's effective, so I'm going to go out and test a whole bunch of people. I just came up with something for fun in my lab at home. I'm going to test a whole bunch of people and see if it has any effect on them. Oh, wow, it cures cancer. No, I'm pretty sure nothing ever worked that way in the history of the world. So we've come up with all of this to figure out how to test Graham, and you haven't shot a free throw yet, have you? So now we're going to have him go out and shoot. Now, how many should he shoot? Well, remember, it's time and money is the biggest obstacle you have. Is shooting free throws going to cost us any money? Is it going to take us days, weeks, months, or maybe minutes? Maybe an hour? Yeah, we could shoot a lot of free throws. Do you agree? That's the easy part. Shooting a lot of free throws. So, what we're going to have him do is go out and shoot a whole bunch of free throws. Okay? So, let's say, let X equal the number of made free throws. Oops, yeah, can't draw. Made free throws. Okay, so he's going to go out and shoot. Let's make it simple. He went out and shot 100 free throws, and he made 75 of them. Excuse me. 100 free throws, and he made 75. I want to bring up the textbook real quick. Ooh, why is it not there? There we go. This thing's going incredibly slow today. Oh, it almost let me in. Whoops, whoops, whoa, 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 whoa. Got an extra thing in my name. Hold on. Try this one more time. Okay. I just want to go, I want to show you guys something. So I want to show you where it is in the textbook too. This is a place that's a little bit confusing because we have a formula. We have a straight up formula for calculating the z. But it's the formula for calculating the z when I know what p is. Do I know what p is?
Yes. No. It's 80, right?
No,
Well,
we think
that's
it's
the
50.
claimed value of p, but is that the actual value of p?
Okay, no. Wait, yes, we do know. It'd be 75.
But that would be his measured p. So this is what I'm saying. What do we know about, how do we compute a z-score when there's a p involved? You guys remember?
Inequality.
I'm trying to bring it up for you. When there's a p involved, we know that agreed? We know these things. And so what do? We do, well, here's kind of the tricky part. This is the mean standard deviation, but if I'm actually going out and shooting free throws, there's not really a mean. So what I'm really doing is, if I divide everything here by n, if I take and divide to get the p, then what happens if I take sigma n, I divide it by n? I'm going to show you something. PQ, this is PQ over n. And that should look familiar. Oh, that's what we did earlier when we were trying to figure out a confidence interval. Remember, that was the plus or minus? We did the z value times this. It's basically just sigma divided by n. Why? Because if I say go out and shoot free throws and you made 75, 75 is not a p-value. 75 over 100 is the p-value, but I really need to compare the p-values. So what we're going to do is we're going to go out and say, we're going to give you benefit of the doubt that you actually shoot 80%. We're going to start with that being the law. This sounds backwards at first. We're going to start by saying we're going to assume that's the truth, and then we're going to let the evidence tell us otherwise. If the evidence is too far away, then we'll reject that. I'm going to start by assuming you're not guilty, and I'm going to let the evidence determine whether we change our mind or not. Does that sound more familiar? That's how a court of law works. We don't start by assuming you're guilty and see if the evidence shows the other way. We start by assuming you're not guilty, because you said, I didn't do it. Okay, let's assume this is the truth, and let's see if the evidence tells us otherwise. We start by saying, let's assume he really is 80%, and let's see if the evidence tells us otherwise. Does that make some sense? So what are we going to use in our calculation then? So the z-value, when we're calculating it, the z star, is going to be the difference between what we saw and what we're assuming. Now, we used this term before. P hat is 75 over 100. P hat is what we actually observe. We've used that term before. We're using a different symbol here because what is the P that we're starting with as the bottom line? We're starting by assuming P is 0.8. Now, what if he went out and he shot? What if he actually shot exactly 80%? Would we even bother continuing in the problem? He claims to be 80, he went out and shot 80. Okay, I think we're done. That's kind of easy. But, you know, so we're gonna test this number versus that number. And so the z-value is gonna be the p hat minus the claimed p. But if we're assuming p is true, then we use pq over n, the claimed value of p, not the measured value. So we're going to still treat P as the law, but when he goes out and shoots, if what he actually shoots is way, way worse or way, way better, then it would give us a large z-value, positive or negative. So do you notice we keep these guys? Now, if I shoot a small sample, if n is small, then this number will be, well, if n is small, then this number is going to be small. If n is large, then this number is going to be large. Why? Because a small n means a big denominator. A big N means a small denominator. Oh, so if he goes out and shoots a bazillion free throws, I have more evidence. That's why you always take the biggest sample you can afford to take. Let's just say 100 free throws was enough. Your arms are getting tired. Okay. So this is what we're gonna measure. So in this problem, my p hat is 75 over 100. So my z star is 75 over 100. Obviously, that's 0.75. Minus the claimed value over the square root of the claimed value. What would Q be? If we're assuming he's an 80% free throw shooter, then Q is 0.2. Yeah, it's how many does he miss? And then my sample was 100. Let's calculate this value. It should be a negative number. And let's calculate this. Tell me when you get a number. It actually comes out really nice in this case.
I have negative 1.25.
Negative 1.25. Everyone get that? That's a fairly big negative z-value. That's fairly big. Now let's go back to our picture. There's 0. There's negative 1.645, right? This is the shark-infested lava. This is you went full speed and where did he end up? I don't know, maybe about right here. Does everyone agree? That's about where he ended up. Do we reject the null hypothesis or do we not reject the null hypothesis? Did we reach the shark-infested lava? No, we did not. So this is, you guys are going to get used to this. This is what we're doing for the next couple weeks. But I want you to understand the theory behind it, and the language is also really important. You don't say I accept, you say I reject or I fail to reject. In a court of law, you say guilty or not guilty. You don't say innocent. Okay? That's not one of the alternatives. Is the person guilty or are they not guilty? By the way, if they're not guilty, can they still be mostly guilty? Yeah, in fact, they probably are. Right? So, what is our conclusion? Our conclusion is we fail to reject the null hypothesis. You can just write H0. He wasn't quite bad enough. Okay? He wasn't quite bad enough. We failed to reject the null hypothesis. Does that mean we absolutely believe him? You were on trial and they found you not guilty. Do we now actually believe you're innocent? Or is it more there just wasn't enough there to prove your guilt? That's usually actually the right conclusion. So how we word the next thing is very important. Here's the way I like to tell people. You're now going to have a press conference. You're the mic and the whole, everybody's out for you. You know, Graham's been kind of on trial for his free throw claims. And you're going to have a press conference. And you're going to say, we just ran a test. We failed to reject the null. Graham absolutely is an 80% free throw shooter. I don't know, I'd say that because you didn't shoot 80%. So there's two things you could say at this point. Yeah, absolutely you believe he's 80%. Or there's just not enough evidence to say otherwise. Which one is it?
Not enough evidence.
There's not enough evidence to say it. You're not guilty because there was not enough evidence to convict you. We don't believe you're innocent, but there was not enough evidence to convict you, so now we're done, you move on. Okay? So the conclusion is fail to reject the null. There's not enough, and by the way, that's the usual. Not enough evidence to conclude he is less than 80%. When you fail to reject the null hypothesis, you cannot say the alternative is the truth. You can't. You can't say, we found you not guilty, but we're going to call you guilty anyway. No. If you fail to reject the null hypothesis, that's like saying we found you not guilty. So therefore, you said there's not enough evidence to make this conclusion. Now let me change things on you. What if Graham went out and shot 85 out of 100? What if he shot 85 out of 100? Then I'd have a positive 1.25, wouldn't I? And where would I be in my picture? I'd be way over here. Now, you failed to reject the null, but wouldn't this be really, really, really strong evidence that he really is that good? If he went out and shot better? So if he went out and made 85 out of 100, not only would you, again, you'd fail to reject the null, but wouldn't you say, yeah, he is better than 80%. I mean, that's kind of a slam dunk. Yeah, you are that good. It is possible to have that situation, okay? But often it's the case where it's a close call. Now, he shot 75 out of 100. He made 75% of his attempts. But that wasn't enough. Because, you shoot 100 shots, just a few of them rolled out. So let me change that on you. I'm going to change something. He made 75 out of 100. That wasn't that far off from 80 out of 100. What if he makes 750 out of 1,000? Would you say that's a large sample? Yeah, that would be an outrageous sample. Now, 750 is quite a ways from 800. Do you agree? So you might have had a few roll out, but you are really far from 800. But you still made 75%, but in a ridiculously large sample. What would change in all of this? One thing. That's the only thing that would change. Well, the calculation would change. So tell me, what is the new calculation? This is pretty powerful, by the way.
Maybe 3.95.
Oh my goodness. Do you know where you are now? You're about here. You didn't just go into the shark-infested lava. You were rocket launched way out into the shark-infested lava. You did an Evel Knievel. You went up the ramp, landed 1,000 feet out in the shark. Now what would we say?
We do reject.
Would you say reject or fail to reject? Now you would say reject the null hypothesis. When you reject the null hypothesis, you have one conclusion and one conclusion only, that the alternative hypothesis now is the truth. We rejected your claim of being not guilty. So what's the conclusion? You're guilty. We don't say, well, we're still looking at it. No, you went to trial, you're either not guilty or you're guilty. We reject the idea of not guilty. You are guilty. So what would we now say is the conclusion? In this case, we'd say he shoots less than 80%. We just keep it real simple, okay? Now, I have fun with some of the answers I get because a lot of times we sound like lawyers. We'll say, well, based on the circumstantial evidence, it's reasonable to conclude that he might be, we fill a page with words, and in the end I'll say, so what exactly did you say? Was he guilty or was he not guilty? Reject or fail to reject, and then your conclusion. Keep it really simple, right? Don't over-explain it because you want anybody who's listening to understand exactly what you just said. Now, here's the crazy thing about that. We did 2 situations where you shot 75% in your sample. Now, in a small sample, 75% is not that different from 80%. Think of it a different way. You went out and you shot 5 shots. If you make 4 of them, that's 80%. If you make 3 of them, that's only 60%. 60% is way far, but it was only 1 basket difference. There's only 1 shot difference. You're not gonna reject. But if I go out and shoot a ton of things, I was 50 baskets different now, wasn't I? So the more the N is, the more powerful. That's why you always want a bigger N. So let's go back to the first problem. Now, I'm going to go back to this one. Okay. Because now there's another thing in here, and this also helps us understand it. Because a lot of you will say, this is a pretty big negative z-score. I mean, he didn't make 80%, he was way less, but he wasn't way less enough. So now there's another thing that we throw in, and in a lot of situations from a statistical standpoint, this is the thing that people use the most, and it's something called the p-value. I'm going to put it up here. The p-value. The p-value it's a really simple concept. If he's telling the truth, and he really is an 80% free throw shooter, is he always going to make 80% of his free throws? No. There's going to be days when you make less. There's going to be days when you make more. So if he was truly an 80% free throw shooter, if the null hypothesis is actually the truth, then how likely is a result this extreme or more? So what we want to do to find the p-value, we want to say, what is the probability that z is more negative than this? Why more negative? Because that's the direction I'm going. This extreme or more. Now let's look this up in our z-table. What is the probability in your z-table of z being less than or equal to? So hopefully we're all looking at the same thing. So in your z-table, the probability of being that extreme or more is what number?
0.1056.
0.1056. Here's what this means in English. If Graham is truly an 80% free throw shooter or better, he can have results this bad. Because we'd say this is not good if he's 80% free throw shooter. He can have results this bad or worse still about 10.5% of the time. That's what it means. So is this completely outrageous? If let's just say every time you go out and you shoot 100 free throws, that means you're going to have this bad a result about 1 out of every 10 times that you go out and you shoot your free throws. So is that outrageous? No, it's pretty far, but it's not outrageous. Now, here's another way of thinking about it. Our criteria, we set at the 5% level. You will always reject the null hypothesis if your p-value is smaller than this. Now think about this. Look at the picture. In my picture, the negative 1.645 corresponded to a 5% tail. So if my calculated z-value was to the left of this, then the p-value would be the probability of still being further to the left, which would be now smaller than 0.05. Does that make sense? So in a research-oriented world, p-value is pretty much what they always use. What is the p-value? Because the p-value tells me everything I need to know about how likely or unlikely was this result. Okay? So we're gonna keep going. I introduced a whole lot of new things to you today. So here's the thing. Somebody, and it usually involves the term claim. Now, people mistakenly think the claim is a null hypothesis. No, the null hypothesis is whatever has the equal sign. More often than not, it's going to involve the claim, but, you know, whatever involves the equal sign. So there's something out there that I can test. It's because mainly I don't believe it's true. I don't believe it's true. Now, I'm going to start with another really simple one. All right? Let's say you've been watching football. You watch football all the time, and you notice the coin flip before the game, the coin flip for overtime. Does not seem like it always lands heads and tails the same amount of times. Anybody ever watch football? Right, what's the expression in football? Do you know it when you're choosing? Actually, in football, they have an expression that I've heard most of my life.
Heads or tails?
Yeah, do you know what the expression is?
Tails never fail.
Tails never fail. Why would anybody say something so crazy? Because statistically speaking, I think the number's around 52 or 53% of all of the coin flips in NFL history. That's the tails. Yeah, tails happen more often than heads in the NFL. It doesn't make any sense whatsoever, but that's why the expression tails never fails. So over time, you pick tails. Just pick tails every time. Is it going to land tails every time? No. But for some reason, it seems to land tails most. So you don't trust that NFL coin. You're saying, I don't know that it lands tails 50% of the time. But I don't know if it's better or not. Because, see, they just got a new coin. The old coin, somebody stole it. So they just got a new coin. They borrowed Dilden's coin. They're now going to use your coin. Could be a Harvey Dent coin. You know what that is, right? It's tails on both sides. But it could be a fair coin. So here's the thing. You think your coin may not be fair. It's that simple. You think your coin might not be fair, but you don't know which way it's leaning. You don't know if it's leaning more towards heads or towards tails. You just don't think it's fair. Let's make it simple. Let's say we're counting tails. We've got to count something. All right? So let's say we're going to count tails. We could count heads. So a fair coin has a probability of what? 0.5. An unfair coin would have a probability not 0.5. Good. Does it matter which way it is? Do you say, oh, I get tails most of the time, so that's okay? No, you'd say it's not a fair coin. If you got one most of the time, it's not a fair coin. It should be exactly the same in terms of the probability. So my probability of success should be exactly 0.5. So therefore, what's my alternative?
Not equal to 0.5.
Not equal to 0.5. Good. Do I care which way it leans? No. We used this example last week. If you got on a scale, you just want to know if it's accurate or not. You don't go, oh, it's okay, it weighs a little heavy. I don't mind. No, I just want to know, is it accurate or is it not accurate? Is my coin fair or is it not fair? Oh, but it's okay if it leans more in this direction? No, it's not a fair coin if it leans more in one direction. So let's test. Again, let's test at the 05 level. But this test now looks different. You have not gone out and flipped the coin yet. You don't know which way it leans. You don't know if it leans at all, but what are you going to reject? You're going to reject if you're here or if you're here. Do you remember what we called this one?
Two-tail?
Two-tailed test. This is a two-tailed test. You're going to reject if you're in either extreme. So if the alpha level is 0.05, then that means I have half of it here and half of it here. So that means I need the z that goes with 0.25, and that one is the most common one. Which one's that one?
That's the 1.96.
This is the 1.96. So here, that's a z-value of 1.96. Over here, that would be a z-value of negative 1.96. Okay? This feels a lot like a confidence interval in that sense, doesn't it? Okay. So, we have not even flipped the coin yet. We will reject the null hypothesis if our measured value of z is what?
Less than
Less than
negative 1.96.
negative 196 or
Greater than 1.96.
positive 1.96. The inequalities and the signs are absolutely critical. If I get the inequality backwards, then I'm going to reject most all the outcomes. I only want to reject the extremes. So if I go out and flip a coin, if I go out and I flipped a coin 10 times, is 6 tails or 6 heads outrageous? Or is that very likely? A fair coin. If I go out and flip a coin 1,000 times, 600 heads or 600 tails is extremely unlikely. It's way too far from half. Okay, so the larger my sample, the more the evidence is just sitting right in front of me. All right? So, you're going to go out there and you're going to flip the coin. Now, we're counting tails. So you went out there and you flipped the coin, and for some reason you were distracted. You wanted to flip it at exactly 100 or exactly 500 or exactly 1,000. You wanted some really nice clean number. But it didn't happen. You ended up flipping at 371 times. It just happened that way. And your number of successes was 178. Okay? That means you had 178 tails. I don't know. Is that a lot? Is that not enough? That's what you did. Do we have enough evidence to test it? 371 coin flips, would you say that's a pretty good size sample? Yeah, it's huge. Huge sample. He shot 100 free throws. That was large. So this is like 371 free throws in a sense. I mean, how long does it take you? This is only maybe 5 minutes it took you to do this. So, now what? Our Z star is, okay, PQ. I'm going to leave them as quotients. I'm not going to calculate them as decimals and then write a rounded off decimal into my square root. Way too inaccurate. No, just leave the fraction. You're doing the whole thing on your calculator. So just leave things as fractions. Everybody okay with that? The only decimal I'm going to put in the problem is the 0.5. That's the only thing I'm going to put in the problem. So my p hat, what is p hat exactly?
178 over 371.
Now be careful, what's q hat? Well, if that's the number of tails, then how many heads were there?
193.
193. That's important. My numerators have to add up to 371, or my fractions have to add up to 1. I need both of those because those go right here. So I have 178 over 371 times 193 over 371, and then my denominator is 371. So I need my parentheses key, but it's actually a fairly simple calculation. Now what's my numerator? 178 over 371 minus 0.5. By the way, you need an open parenthesis here and a closed parenthesis here. You don't actually need to put parentheses around anything else in the numerator. Your order of operations, when I go this divided by this times this divided by this divided by... No, it's going to do the right thing. I'm only putting parentheses here because it makes it easier to read. I could write this without parentheses. I just need one here and one here to tell my calculator to leave everything inside the square root. That's where you need the parentheses. All right, so let's do this. Tell me when you get a number. This is a z value, so we'll go 2 places. Young, could you prop that door open again? I think we're okay. Just the air is so stuffy in here. Tell me when you get a number.
Okay. I have negative 0.78.
Does anyone else get that? Good, that's what I got. Negative 0.78. Okay, so in my picture, and again, I always like doing a picture because it makes it fairly easy. My outcome is probably about here. Did I get exactly half? Well, no, you're never going to get exactly half. You just don't want to be too far from half. Now, the question is this a fair coin or not? What would cause you to say this is not a fair coin? If you had an outcome in this tail, or you had an outcome in this tail, you would say it's not a fair coin. Again, it doesn't matter, is it more heads or more tails? You just say it's not a fair coin. We fell in here. Are we very close to rejecting the null? Not really. No, not really. Yeah, you got way more heads than you did tails, but was it enough to say it's not a fair coin? No, not in this case. So what is my conclusion? Let's write it over here. There's a whole series of things that we say now. By the way, this is the only calculation in the entire problem. Most hypothesis testing, you have one calculation. You're calculating a z, a t, or a chi-square, depending on what you're testing. If you're testing mu, it's usually t. If you're testing sigma, it's always chi-square. If you're testing p, it's always z. You're doing one calculation. But all of this setup we did was before we even considered the calculation. We're setting up the criteria. What's going to cause us to make the right conclusion or the wrong, well, never the wrong conclusion, hopefully. So, reject or fail to reject the null?
Failed to reject.
Fail to reject. We're really not that close. So we fail to reject the null. Now, you could argue that you're close enough to the middle that you're okay saying, it's reasonable that this is a fair coin. I'm going to give that as an option. I like using the word reasonable. Can you absolutely say it's a fair coin? Or is it possible it's still an unfair coin, we just had these lucky results? Ooh. So I like using words like it's reasonable that the coin is fair. That would be one conclusion. The other conclusion is not enough evidence evidence to conclude the coin is not fair. We failed to reject the null, so that the coin's not guilty. You cannot say the coin is unfair. Can't say that. You could say, you know what, that result is close enough to the middle that I think it's totally okay to say the coin is fair. I'm totally okay accepting this is a fair coin. Or you could say, I'm not convinced, but there's clearly not enough evidence. The not enough evidence is always the safest conclusion, by the way. The closer my sample got to the center, the more likely you're going to say, I believe it's a fair coin. You with me on that one? But you don't say both of these, one or the other. Right? I believe it's actually a fair coin, or then there's just not enough evidence to conclude it's not a fair coin. The second one is the safe one, but sometimes it's cool to commit to something. I'm backing this coin all the way. Now the last part of it is the p-value. If this is a fair coin, and that's the thing, if the null hypothesis is true, then what is the probability of a result this extreme or more? That means you got to go in the same direction. So that would be what is this area right here? So the p-value is the probability that z is what? Less than your calculated z. Because if I said the probability z is more, then I'm going in the wrong direction. You always go towards the extreme. Now, there's one more piece to this. I'm not quite there. When it's a two-tailed test, because what if I had said, let's count heads instead of tails? Then wouldn't that number be positive and we'd be going the other way? In a two-tailed test, you actually double the p-value. Because you say, what's the probability of a result this extreme or more? But in either direction, because I would have rejected in either direction. So in a sense, in other words, you're also looking at this. Only in a two-tailed test do you do this. And the reason is because we cut this in half and we say we're going to reject in either direction. So what's the probability of result this extreme or more in either direction? Because again, we could have been counting heads, in which case we were going in the other direction. So when we calculate this probability, use your z-score, what's negative 7, 8 gonna give us?
0.2177.
0.2177. So my answer is 2 times 0.2177. You're gonna like this. That's 0.4354. If this coin is absolutely fair, then I can expect a result this extreme or more darn near close to half the time. Whoa. If this coin is fair, I can be this far away almost half the time. Does that make you even more likely to say, yeah, I think this is a fair coin? That a fair coin can be this extreme or more 43.5% of the time. Wow. That's really large number, isn't it, in terms of probability? So that's one of the reasons the p-value, people use this. I know people that have had classes, could be not statistics classes, science classes where the instructor made them run all sorts of tests and they had to use the computer, they didn't know what the heck they're doing, and in the end they always calculated a p-value. And they were asking, what does the p-value mean? That's how likely this result is if the null hypothesis is true. Now, if the p-value is microscopic, then you don't believe the null is true. Okay? So, let's try another one. All right, so you were in a recent poll. Most, let's say, okay, there's some pretty serious stuff going on here. So in a recent poll, it's reported that at most 60% of San Diegans like sunny days. You believe is much more. Okay? Pretty controversial stuff, I know, but you guys are risk takers. So, you're going to go out and conduct your own poll. You do your own unbiased poll. Okay? And the question is real simple. This is a P. Do you like sunny days or not? There's no degree here. It's yes or no. That's what, did you make the free throw or not? Did it land tails or not? The nice thing about things like opinion polls, it's not a degree. If I said, rate the restaurant on a scale from 0 to 10, no, that's not a P. That's something else. Nope. Did you like the restaurant, yes or no? Does everybody understand that there's only two outcomes? It's a 0 or a 1, a true or a false, a yes or a no. You believe there's much more. So we want to test this one because, this is some serious stuff going down now. We really want to get this one right because, if San Diegans don't like sunny days, then we're going to figure out a way to, tone down the sun. We're going to make San Diego into Mordor or something. I don't know. You guys see that Lord of the Rings thing? Anybody watch that? Yeah. The creation of Mordor. It's pretty gnarly. I think we have to have a volcano though. I don't think we have any volcanoes around. But anyway, so this is what we're doing here. So let's look and see what does this look like. Well, P is the probability somebody likes a sunny day. So what's the null hypothesis? If we're saying, if the research said at most 60% of San Diegans like sunny days.
Greater than or equal to?
Such certainty in that. At most means that much or less. So less than or equal to 0.60. See, if they're saying at most 60% and our evidence comes at 40%, then they're telling the truth. If they say at most 60% and the evidence comes out at 90%, then no, they're wrong. So at most means that much or less. So what's our alternative?
Greater than.
Greater than. what is the z value that corresponds with a 1% tail, because this is a one-tailed test. How do you know if it's a one-tailed test? Because my alternative is only in one direction. When the alternative is not equal, then it's in two directions. Okay, so it's a one-tailed test. What is z of 0.01? It's one of our magic numbers.
200.
No.
Oh, is that right? 576?
No, that's 005.
Oh.
You guys got them written
Oh,
on your table.
is it 3? Yeah.
326.
Yeah, that's it.
You got them in multiple places. By the way, if you don't have your formulas in front of you, look at the bottom of the T table. And the reason you look at the bottom of the T table is the T table gives everything to 3 decimal places. At the bottom of the T table, all of our magic Z numbers. You're going, why are our magic Z numbers at the bottom of the T table? Because what's the last row of the T table? Large. You know what that literally means? Infinitely large. T becomes Z as the sample size grows without bound. It's a calculus thing. But the bottom of the T table, they turned into Z values at the very bottom, because that's what large is. Large literally means infinite in that case. But the nice thing about the T table is they're all given to 3 places. So our 196 actually comes out as 1.960, which is correct. So, what does our picture look like this time? Well, which way are we going to reject, left tail or right tail?
Oh, right tail.
Right tail, because my alternative is a greater than. So I'm going to reject out here any calculated z value that is bigger than this will cause me to reject. Agreed? Everybody got that? So any calculated z that is larger than that. So, we've set up the entire problem, and we haven't actually done anything yet. Okay? We've set up our criteria for rejection. We've set up our entire hypothesis test. Now, at some point, we got to go out and collect the data. So, in real life, you're the statistician. You did all of this. You have underlings that you're going to say, now, I want you to go out and I want you to conduct a poll, go all over the county, and have lots of people going lots of places. Why? So we can get it stratified if possible. We can get an unbiased sample that's huge. That's a perfect world, because opinion polls are easy because they don't take money. They take a little bit of time because we want to ask a lot of people, but do you like sunny days? Yes or no? I don't need any information. Yes. Now, can I trust that you're telling me the truth? I kind of have to. Do you agree? That's the one thing. Yeah. It's kind of like when I say, who are you going to vote for president, and you tell me, and then I report in the poll, okay, this is the percentage of people that are going to vote this way. When I'm asking you the question, you tell me who you're going to vote for, I have to assume you're telling me who you're going to vote for. I have to assume you're not lying to me, because what would be the, if I actually thought you were lying to me every time I asked somebody a question, then all opinion polls would be invalid, wouldn't they? Because I don't trust any of the information. No, of course I have to believe that what you're telling me is the truth, because that's what I'm doing. I'm reporting what people just told me. So we're going to go out and we're going to collect a sample. So let's say we go out and we collect a really big sample. So our sample, by the way, X is the number of people who like sunny days. You like sunny days, yes or no? We're counting the yes votes. So we're going to call a success a yes. If you say no, we'll call that a failure. So I'm going to go out and I have the opportunity to ask 200 people. And in that 200 people, let's say that 142 of them said, yes, we like sunny days. Okay? Do we have enough information here now to run our test? What is our p hat?
142 over 200.
142 over 200. Is that a terminating decimal? It's over 200.
Yes.
Yes. So what will be easier in the calculator? Entering the fraction or entering the decimal?
Yes.
Probably the decimal. The only time, this is an absolute, the only time you get to convert it to a decimal is if it's a terminating decimal. If you're having to round it off and then you're using another rounded off number, and you're going to have compromised decimals. Your last, let me put it another way, your last decimal place is always going to be incorrect. And that might make the difference. So if you're not sure, leave it as a fraction, but if it's a terminating decimal, go ahead and do this. Because that makes Q hat, which would be 58 over 200, or 0.29. Remember, those just got to add up to 1. So now my calculated Z is now what's going on top? This. Again, leaving it as a fraction or leaving it as a terminating decimal won't change anything. Okay. Tell me when you get it back. It's important. No one yell out your answer yet. Just wave at me if you have a number. Because I want everyone to have the opportunity. This is not complicated, but there's just enough button pushing that a lot of us are not getting the right answer because we're not, there's a parenthesis missing or something crazy is happening. I want to know, everybody's entering this into the calculator. I want to know that we're all getting the same result. What do you think?
Can you give me help on that? I feel like I keep doing it wrong.
We'll go parentheses numerator. So 0.71 minus 0.60, close parentheses. Okay, divided by square root. Open parentheses, and then just do this. 0.71 times 0.29 divided by 200, close parentheses. Okay, hold on. Yeah, I think that's right. What do you got? Yep, I think you guys are getting the right answer. So what do you got, everyone?
3.42.
428, so 4.3. You're kind of out here somewhere, aren't you? Shark infested lava? Yeah, you're toast. You're way out there. Okay. We love results like this. We actually love this kind of result. If my result falls anywhere in here, it's kind of gray area, isn't it? It's like, you were almost guilty. It's like, you're that close to being guilty, but no, this is pretty easy. We love it when it's way out there because there's no gray area. It's absolute. It's really easy to make our conclusion. There's nothing worse than a nebulous conclusion where it goes, it's kind of iffy. I'm not sure which way I'm leaning because it wasn't convincing. This is convincing. So what's our conclusion? Here's what I'm going to write, by the way. This is greater than 2.326, which was the criteria I needed. So it makes my conclusion really, really simple. What is my conclusion? Reject the null hypothesis. You are guilty. So if we reject the null hypothesis, we're going to have a press conference later. What are we going to tell the world is the truth? When you reject the null, what are you saying is the truth? In no uncertain terms, the alternative is the truth. That's how it works. When somebody, when we rejected your plea of not guilty, we found you guilty. We don't say, well, you're probably guilty. There's a really good chance you're guilty. No, you're guilty. We're done. You are guilty. Now you pay the price. We rejected the null hypothesis. What is the truth? By the way, don't tell me the answer is NP is greater than 0.6. What was the whole point? We said at most 60% of San Diegans like sunny days. We're not saying that's not the truth. So in words, what is the truth? More than 60% of San Diegans like sunny days. Let's actually use words to express it. We expressed as a mathematical inequality what that is. This statement here means less than 60% of San Diegans like sunny days. This statement means more than 60% like sunny days. But let's use the words. You wouldn't say, reject the null P greater than 0.6. And your viewing audience is going to go, and what does that mean exactly? So use words, reject the null, more than 60% of San Diegans like sunny days. You with me on that? Is it possible mathematically that this result is inaccurate? Is it possible? I went out and collected this poll correctly, but is it possible it's a bad sample? In fact, what is the probability of a bad sample? Anybody know? That's what alpha is. Alpha is exactly the probability of a bad sample. That means if your alpha is 0.5, you could have a bad sample 5% of the time, but you're okay saying 95% of the time I got it right. If your alpha is 0.1, that means there's still a chance. 1 out of 100 times that we're doing this, we could have got it wrong. That's always a possibility. Now, we're going to calculate the p-value, and that's going to be really, really convincing. The p-value is what is the probability of a result as extreme as ours or more. So now we'd be looking in this direction. So for this problem here, I want to go with. All right, so the p-value is the probability that z is bigger than or smaller than this number. Remember, it's this extreme or more. But we're already going in that direction, so it's the probability z is larger than. Here's why. If I said the probability z is smaller than this, that's almost 1. Right? Because that's almost every... No, p-values should be tiny. So when I look this up in the table, oh, that's going to be 1 minus the probability that z is smaller than. So let's find that number in the table. This is going to be absolutely convincing evidence now. 3.43 in my table. 9997? So what is that number? 0003. In simple English, if the null hypothesis were actually true, if at most 60% of San Diegans like sunny days, then a result this extreme or more will happen this often. That's microscopic, isn't it? Does that make you even more sure that your results are correct? It should. That's the whole point. You're never going to get a p-value of 0. Because no matter how obvious something is, there's always that 1 in a bazillion chance. Our p-value, well, that would be 1, this is, right, this would be 3%, 3/10, that's 0.03%. I mean, that's really microscopic odds. So if this were the truth, that's the probability of this happening. You'd say, no, that ain't happening. That ain't happening. That's not even a possibility in a sense. So we're really sure. Now remember the p-value, if the p-value is smaller than alpha, you rejected it. 0.0003 is way smaller than this. That's why we rejected it. If the p-value is bigger than alpha, we don't reject. But if the p-value is bigger than alpha but close, I got right up to the edge of the shark-infested lava, that's the result we hate. We hate that result because it feels like we're compromising. It's, oh my gosh. And really it comes down to this. A lot of times if I just had a bigger sample, I might have been able to reject. But you don't get to do it again. Here's the thing. If you came really close to rejecting something, you say, well, if I just do a bigger sample, you should have taken a bigger sample the first time. In real life, you don't get to do that. Well, we didn't have enough evidence to find you guilty this time, so let's try you again and let's see if we can get more evidence. You don't get to do that in real life. Do you know that? It's called double jeopardy. You can't be tried twice for the same crime. That's why you got to get it right the first time. You can't do the same hypothesis test on the same thing a second time. Well, I'll just take a bigger sample. You should have taken the bigger sample the first time. You don't get to do it a second time, especially if I'm trying to disprove something. You know, you made a claim and I'm trying to disprove you. I'm trying to show you are not telling the truth. And I couldn't do it this time, so now I'll try it again. No, give up, walk away, move on to the next thing. Yeah, you don't get to keep doing it until you get the result you want. It's not how it works in real life. So hypothesis testing on a P is actually a fairly simple thing. Now let's do it in the order of things. I have to correctly state my known alternative. Because if I don't get these right, then my conclusions may be the opposite of what they should be. Then I state what is my criteria for rejecting the null hypothesis based on the alpha level. You don't decide the alpha level, that's always told to you. You're always told, at this level of significance. That's also the term. At this level of significance, that's the alpha level. Now, is it a one or two tailed test? That matters. Okay? You don't have to draw the picture. I always draw the picture so I can see visually, what am I going to reject? Oh, I'm going to reject in the right tail this time. Okay? And at some point, I have to have my data. And then when I do have my data, I can calculate my z star. That's the only calculation in the problem. Then it's basically, where does it fall? Do I reject or do I fail to reject? If I reject, then the alternative is the truth, period. If I fail to reject, then I have a little bit of leeway how I want to say it. Let's throw a what if. What if this calculated value was just a little bit less than this? What if the calculated value was, like right here? What would you have said, first of all?
Fail to reject.
Fail to reject. Does that mean you overwhelmingly are accepting this? If your calculated value is right here, that means your sample was way over 60%. My sample was 71%. What if your sample was like 65% or 66%? You may not have rejected. Oh, I have a sample that's way more than 60%, but just not way more enough. That's where you decide. You don't say, oh, they're telling the truth. You just say there's not enough evidence to say they're not telling the truth. You don't say they're innocent. You just say there's not enough evidence to say they're guilty. You all realize that's not the, those are two different statements. To say innocent and to say not enough evidence to conclude guilt are pretty extreme, but in both cases it's not guilt. So not guilt could be almost guilty all the way to innocent. But it depends now, again, on the calculation and how close. Any question on this? Yeah, let's see if we can get one more example in, because I want you guys to feel good about this, because when we move on to the next thing, and then the next thing, it's going to have the same structure, but the calculations will look different because of what we're calculating. But the big picture will be very, very similar. Okay, so let's say that Ava claims she is the best guesser on multiple choice tests. She claims that she doesn't even have to prepare for multiple choice tests. She just goes in and nails them. She accidentally walked into a Russian language class multiple choice test and she still nailed it. Right? She's just an unbelievable guesser. Right? She has insight that we don't have. Now, Ricardo was in the same class and goes, I don't buy it. I don't think she was guessing at all. I think she knows what's going on. So Ava even proved that she took the test blindfolded. Didn't even read the questions, just started filling out the bubbles. Okay, have some fun with this one. So, make it simple. We need a number. So she says she's a great guesser. We say, how good? So she says, on 5 response tests, you know what I mean by 5 response, A, B, C, D, or E. She scores at least, let's say, 35%. Now remember, just an average guesser would get 20%. Agreed? 1 in 5. But she says, no, she gets almost twice as much as, that's incredible. That is unbelievable. So, she claims to be an incredible guesser. Now, how are you going to test this? How will we test this? Have her take a random multiple choice test that she doesn't know anything about. I'm going to have you take the contractor's exam. It's a multiple choice test. Do you know a lot about the contractor's exam? Great, that's a perfect one. You know why? Because that's like 1,000 questions too. So that's a really big sample size. So we're going to do that. So the first thing is, what is our null and alternative hypothesis? Now think about this. She says that she gets at least 35% of all of her guesses correct, which is actually pretty incredible. So what is our null hypothesis?
P is greater than or equal to 1 point.
P is greater than or equal to 0.35.
Yeah, that's it.
Exactly. So what's our alternative?
Is less than.
So it really comes down to this. You know, you let her make that claim, but you think that's exaggerated. You think it's way higher. When you're watching commercials on TV and people throw out claims and percentages and stuff like that, you can believe it or you can say, you know what, I think they're exaggerating. I think they're overstating or understating whatever it is, you know, to make themselves look better. Well, that's normal. People do that. But how would you prove it? You have to have a way of actually testing it. So we're going to test her by making her take a random multiple choice test and just see how it goes. So let's test this time at the, how about the 05 level? We've used this value before. So what's Z of 05?
1.645.
1.645. I do not need you guys to have those memorized. I have memorized because I've done this a million times, but I need you to know where they are and not question that you got the right one. There's nothing worse than doing everything in the problem right, but selecting the wrong line in the sand. And if I select the wrong line in the sand and it's a close call, I will get the incorrect conclusion, won't I? Because I'm comparing it to the wrong number. That's why it's important that we get this piece correct. So I am going to reject in the right tail, aren't I? Are you sure? I left the pic. This was the picture that was up before. Is that where I'm going to reject?
No, you're gonna look the other way.
I'm going to reject the other way. Yes. Because the previous example was a greater than. Remember, the alternative is less than, which means she's got to be way less than. If, let's say on that contractor's exam, she guesses 34% of them correct. Do we say, aha? Or is that pretty darn close to what she's claiming? She guesses 40% correct. We're going, wow, she's pretty good. She only gets 20% correct. You'd start saying, nah. It's got to be way less before we say, no, there's no way. There's no way. Because again, Steph Curry can still miss 2 free throws in a row and be a 90% free throw shooter. Right? It doesn't have to be absolute. So let's now state our criteria for rejecting. We will reject the null hypothesis when? If our calculated Z is
Is less than 0.3, negative 1.645.
negative, good. Again, the reason I always draw the picture is so I want to get the inequality correct and I want to get the sign correct. What if you accidentally said, and by the way, this is the most common wrong answer on any exam. What if you accidentally said, I'm going to reject if I'm less than 1.645? That means you're going to reject 95% of all possible outcomes, which would be bad. I only want to reject the lowest 5%, not the highest 90. I don't want to reject 95% of the outcomes, I want to reject 5. So the sign is huge. All right, now we put it to the test. Ava is going to take a 1,000-question test. Make it real easy. Let's say X is the number of right answers, because we're measuring correct answers. So she takes a 1,000-question test, and she gets 375 right answers. All right, you ready? So, what is our p hat?
375 over 1,000.
375 over 1,000, which I can certainly do 0.375. What's our q hat? That'd be 625 over 1,000 or 625. Okay? Doesn't matter if you go fraction or decimal. The order of subtraction is critical. It's always the measured value of p minus the hypothesized value. The hypothesized value, I'll go back and remind you, we're starting by assuming this is the truth. We're assuming, no, Ava guesses 35% correct, period. But then we're going to let the evidence tell us if that's not the case. Everybody got it? So we're starting, the truth is the 0.35. So it's always measured minus what we're hypothesizing is the truth. And then in the denominator, again, it's the hypothesized values, not the measured values. So that's why this would be the 0.35, 0.65. Okay? Because if the P is 0.35, then the Q would be 0.65. And how big was my sample? It was 1,000. So let's calculate this. Ooh, that's a perfect answer. I love that answer. Tell me a number.
1.66.
1.66. Oh my gosh, that is so ridiculously close. Wait a minute. Is it? Here's our rejection criteria. Where did we fall? Actually, we fell here. Our rejection criteria was smaller than negative 1.645. What did you actually do? Positive 1.645 or 1.66. Oh, are we close to the shark-infested water? Actually, you know what happened? The shark-infested lava is over here, and we rocket launched Ava in that direction. Ava, you're 1,000,000 miles from the shark-infested lava because you ended up going that way. That number is so close to our critical value, but we're on the wrong end. So therefore, do we reject or fail to reject?
In our denominator, how come it's not the 3.75 or 0.375?
Remember, we're assuming this is the truth.
Okay.
So we use these values. Oh, you know, I think in some of my use, you're right, I should have been using that one. Yeah, I just realized that we did that in another one. Yeah, we should be using that one. Well, I'll fix that one. So, how do we look at this? The evidence was that way. Rejection was that way. Do we reject or do we fail to reject? Reject or fail to reject?
We reject.
We fail to reject because we're not in the rejection direction, we're in the opposite direction. In fact, Ava claims that she guesses at least 35%. Is she telling the truth? She just guessed 37.5% on a 1,000-question test. Yeah, in fact, you could even up your claim if you want. You want to go higher than 35 because that evidence is pretty overwhelming. No, fail to reject, she does guess at least 35%. I just realized that Ashad pointed out, I should have been using the hypothesized P and Q. Now, it's not going to change any of our answers by just the microscopic amount. Now, there's no point in doing a p-value in this case because the probability of a result this extreme or more in that direction, it's like 0.99 kind of thing. No, this one is, so every now and then you get something like this. The evidence overwhelmingly supports the claim. We're not used to that one, are we? We're trying to disprove her, and her evidence is overwhelming that she's telling the truth and that she can make this claim. So here's what happens in real life. I always kind of laugh at this. There's something going on, and there'll be some sort of watchdog agency. Some of the news channels actually have these. They are consumer advocates, they're called. They're protecting you. And somebody's doing something or making some claim, and the news stations have some money, they have some resources, so they'll send their investigators out to look into it, and they will find maybe nefarious activities are taking place. And then they will expose them on the news. Has anybody ever seen stuff like that? It doesn't even matter what it is, that they like to expose them on the news, this place, this organization, this person is not being totally honest with us. So they're going to go out and they're going to check out your claims about what all these things are doing, and then they find out it's better than you're actually claiming. Is that making it to the news, by the way? Not a chance. They were trying to show you were dishonest, corrupt, and it turns out you're like a saint and you're doing all these wonderful things. Now, maybe they'll highlight that, but they were trying to expose you, and it turns out they couldn't expose you. There's no evidence. You only hear about the bad stuff. You never hear about when it's the other way. So this is one of the really weird areas in real life that, it's kind of troubling. We go out and we go after things to see if it's honest or dishonest, and we're trying to prove it. And if it turns out it's overwhelming the other direction, we never hear about that, do we? Now, this is one of the things that happens in real life, and some of you maybe pay attention to things. Somebody has been accused of doing something terrible. And then after all the research and evidence, it comes out, nope, they're completely scot-free. And then you never hear it about again. You only hear about it if they were found to be doing the bad stuff. They were accused of doing bad stuff. It was found, nope, they didn't do anything bad, but then you never hear about that. You ever notice that? You'll ask later, what happened to so-and-so? I thought they had been accused of all these horrible things and it just sort of disappeared. Well, because after doing the investigations and stuff, they didn't find anything. But the accusations were public. They were on TV all over the place. I can think of a few situations in the last several years. The Duke, I think it was the lacrosse team. You guys remember that about 10 years ago? The whole Duke lacrosse team was accused of raping somebody at a party, and this person had all these charges. They went on trial. They were looking at all doing hard time in prison. They'd all been expelled from school, kicked off the teams, all this. And then it came out later that the person making the claim said, I just made it all up. I didn't, Absolutely 100% of it was fabricated and made up. They were all found completely innocent, reinstated. And that never made it to the news. I had to research to find it. These people's lives were completely ruined publicly. Everybody at that university looked at them as being, these are horrible criminals. They should be put in prison the rest of their lives. They didn't do anything. They were accused by somebody. It made national and international news because it was Duke University. Nothing ever happened. And I hear about things like this, fairly common, that the accusations are huge and then nothing ends up happening and we don't hear about the other way. So I'm the watchdog agency and I'm trying to show you're cheating and doing all these things, and I find out, wow, you're doing incredible things. But we accuse you of maybe being dishonest. Shouldn't we come out later and say, you know what, they're really doing great things? It feels like that never happens. So yeah, there's a flaw sometimes in the way we test. So when your evidence actually strongly supports what there is, you just go away. You don't make any more noise. You're trying to disprove you couldn't. It's done. And unfortunately, a lot of times the person who's kind of on trial, right? We never hear about that. Yeah, it was overwhelming in the other direction. All right, let's go ahead and stop. We're going to do some practice. This is our